I hope you had a chance to write insertion sort. I'm going to show you my solution now, and then we're going to do the runtime analysis. So here's my insertion sort. It is a function. It takes as input a list, and we're going to modify the list to be in sorted order. So first thing I'm going to do is just extract the length of the list. I'm going to need that in a few places. And you can see that the body of the function is just a for loop for I in range 1 to n. Notice that I'm skipping the 0th position because I don't have to worry about the 0th position. That's a 0th iteration where that item is inherently sorted. So we're going to start at index 1, move down and insert, then go to index 2, move down and insert. So this for loop will do that iteration looking at the ith element and sliding it down until it finds its home. So let's see how I'm going to do that now. So the first thing I'm going to do is I'm going to grab the element in the ith position. So again, remember that this is the key or the element that I'm going to slide down until it is in the right position. Now, what do I mean by slide down, by the way? I don't mean I swap. It's not a swapping. It's that I've got to move everything to the right and then make a spot for that because I need to keep everything in the same order. All right, let's see how I'm going to do that. So I'm going to set j equal to I minus 1. So let's do this by way of an example because I think it'll be a little bit easier. So here's a list with a bunch of elements in it. Again, just a bunch of integers. Let's say that I is this position. So 0, 1, 2, 3 is that position there. And j is going to be I minus 1, which is just to the left. So that's the first one we're going to compare, and then we're going to compare, and then be done. So I've set key to be 81. That's what's in the ith position. That's that line of code right there. All right, now I've got a little while loop here. So conceptually what this is going to do is keep sliding leftwards until we find the home to insert the key 81. So let's see what the conditions are here. While j is greater than or equal to 0, well, that makes sense. I don't want to run off of the list. So I'm going to keep decrementing j until I get to the very end. And then, obviously, I don't have to go any further than that. There's nowhere to go. So while j is greater than or equal to 0, I'm not at the beginning of the list yet, and the list sub j is greater than key. So let's see if that makes sense. Sure, if this is greater than this one has to go leftward. And as soon as that is not true, and again, by the way, I'm going to assume that all the elements are unique, so I don't have to worry about equality. So as long as this element is greater than this element, that key has to jump over, and then jump over, and jump over. Okay, so what am I going to do if that's the case? So in this iteration, j is certainly greater than 0, it's 2. And the list sub j, 89, is greater than key, which is 81. So I'm going to set the list of j plus 1, which is that element, to be the list of j. Let's see what's going on there. So I set this element to be this element. Notice I've annihilated 81. Right? I haven't swapped them, I've just annihilated it. But that's okay because my key is holding the element that has to be here. So this element is wrong, but this element is right. So we'll hold on to that. We're going to fix that in a second. So I knew that I had to slide 89 this way because I have to make room, but I don't know how many more I have to make room for. So I'm going to hold off the key here, I'm going to move this element here, and I'm going to just leave this here. Okay, now at this point I've got to compare the previous element, so I'm going to decrement j by 1. So j equals j minus 1. Good. Now, we come back to the while loop. While j is greater than 0, sure. The list sub j, that's 85, is greater than the key, 81, sure. So now what do I want to do? I want to move 85 to this position and then decrement j. So the list of j plus 1, that key, that element, is equal to the list of j. So 85 goes there. Again, notice I haven't swapped anything. I've just moved 85 over 1. So now 89 moved over 1 from its original position, 85 moved over 1 from the original position. This is wrong, but we're going to fix that in a little bit. Okay? So now I'm going to decrement j by 1, and then I get back up to the while loop. Is j greater than or equal to 0? Sure. Is the list sub j, 45, greater than key? No, it's not. So I'm done with the while loop. I'm done finding the position. The position where this belongs is 1 to the right. Okay, so now this last bit of code is going to set the record straight here. So it's going to say the list of j plus 1, because I overshot by 1, is equal to key. Sure, because that was the last duplicate entry that we moved over, and now I'm going to slide it right into that position right there. and then I'm done. Okay, so this is, by the way, a clever way of doing this. I could have swapped the positions. So instead of setting this to 89 and leaving an extra 89 here, I could have just swapped it and swapped it and swapped it and swapped it and kept swapping till I get the end. Why did I do it this way? Well, this is only one line of code versus 3 lines of code. The other one would have worked fine. Runtime complexity would have been the same. It's just a slightly elegant solution. So if you didn't get exactly this solution, that's fine. If you had swapped it, a little bit of extra work, but perfectly fine and reasonable solution. All right, let's do the runtime analysis. So you of course have to be able to do this sort of formal analysis, but it's also good to just look at the code and try to get some intuition. Yeah? So you can see that there is this external for loop right here that's running n-1 times because we're going from 1 to n. So there's at least something that is linear. But embedded inside of that is another loop. So it looks like there's going to be, maybe something more than linear, because this thing is going to have to loop for each time this is looping. Yeah? So just some rough intuition for what's happening. So let's go ahead and look at what our runtime complexity is. We have a single line of code here. That's a big O of 1, constant. We have a single line of code here. That's a constant. And then we have a single line of code here. It's a constant. But these things are bundled up inside of a for loop, which is running n-1 times. So this thing happens one off, so we can ignore that. But this O of this line of code, we'll get back to that while loop in a second. And this line of code is at least n. And of course it's n-1, but since I don't care about the constants, I'm going to go ahead and just call that n. Okay. So the bigger the list, the more I have to evaluate that line of code, that line of code, and that line of code at least n times. Now what's happening inside of this while loop? Well, let's see. Inside the bottom of the while loop is just something constant, right? I'm just going to assign a variable and decrement a variable. Yeah? But now the question is, how many times do I loop through that? Well, this is not a for loop. See, a for loop, once I say for I in range 1 to n, I know how far it goes. It's n times. But when I have a while loop, I don't necessarily know, because it depends on the condition, right? It depends. I mean, this one I know because I know I'm going to decrement j, but this one I don't know. I don't know how far I have to move the element. It's determined, it's based on what's in the list. Yeah? So the worst case scenario, though, is that I'm going to take an element at this position and I have to bring it all the way to the beginning, right? That's the worst case scenario. Why? Well, if I pick an element, let's say I've got everything sorted here and I hit the next element and it's the smallest element in the list, I've got to slide it all the way down, which means this thing on each iteration is going, like on the first iteration it's going to have to slide by 1. On the second iteration it's going to have to slide by 2. On the third iteration by 3. By the way, here's a question you should ask yourself. What does that list look like where every single element has to slide all the way down? Yeah, the list is in reversed order, in which case everything has to move all the way down. So in the worst case, this loop will run 1 time on the first iteration, 2 times on the second iteration, 3 times on the third iteration, up to n-1 on the last iteration. Well, that looks pretty familiar. So I've got an O of n, which is this line of code, this line of code, this line of code, this line of code, and this line of code. That's that n right there. And then I've got the inner one. In the worst case scenario is every element has to loop through the whole way when the list is in reverse order. Well, this looks awfully familiar. It's the sum of the first n numbers, which of course is just O of n squared. Now, why did I do that worst case scenario? Why? Well, that's what big O does. Big O says in the limit, in the worst possible situation, what is your runtime going to be? It's going to be O of n squared. But it's worth thinking about at least what happens in the best case. Okay? So let's think about that a little bit. Well, we know we have at least O of n. We're going to have to do that line of code, that line of code, and that line of code. So at a minimum, we still have, this is a for loop. Guaranteed we're going to have to go through this. So at an absolute minimum, we've got big O of n. But what if the list is in sorted order? Well, I'm going to plop an element out, and then I go back in and I'm done. Plop an element out, go back in, I'm done, because it's already in sorted order. So that means this is only going to execute once each time. Ah, that's nice. So if this never spins, the entire algorithm is just big O of n. So if I give you a sorted list, big O of n. If I give you a reverse sorted order, big O of n squared. And if I give you something in between, partially sorted, partially unsorted, well, it's going to be something in between those two. But the algorithm is still big O of n squared because we have to concern ourselves with the worst case scenario. Okay, so worst case scenario, big O, insertion sort and selection sort from the previous lecture are both O of n squared. Not terrible, but not great runtime. But let's just think through selection sort again. So we agree that in the worst case it's O of n squared. So here's selection sort again. I've got my one for loop here and my second for loop here. And again, notice a really subtle difference here. These are nested for loops. Insertion sort had a for loop and a while loop. That while loop had a conditional. And that conditional can bounce out under certain conditions, which is what led to the best case being O of n. But here, no matter what the list is, that's a for loop. You are going to iterate that. Even though there's a conditional here, there is no way of breaking out of this for loop. So the runtime complexity of selection sort is O of n squared. But the best case, let's say the list is in sorted order, what is it? Well, I don't have the ability to know that it's in sorted order. This is a for loop. I've got to run through the whole list doing what I do. And so in the best case, it's O of n squared. So here's an interesting pragmatic issue. I've got selection sort and insertion sort. They're both O of n squared. Period. End of sentence. Done. But in the best case scenario, insertion sort is a little bit better than selection sort. So if you had to pick between these two algorithms that both have big O of n squared, why wouldn't you pick insertion sort? Because every once in a while, it's going to be a win. It's going to be slightly better. So this is where the theoretical bounds, the big O, and the practical issues of runtime complexity diverge a little bit. Absolutely, the algorithms are big O of n squared, but practically speaking, there will be times when your list is not actually that unsorted. There's only a few things out of order, in which case insertion sort is actually absolutely the right thing to do. Okay, good. So we have two algorithms for big O of n squared sorting, and I could do dozens and dozens of lectures on this, talking about big O of n squared sorting algorithms. There's lots and lots and lots of them, but n squared is not great. It actually gets pretty costly. The cost scales with the square of the length of the list, and that's pretty costly when you're starting to deal with billions and hundreds of billions of entries. And so the question is, can we do better? And when we come back, we're going to try to do a little bit better than n squared with a couple of new sorting algorithms. So we'll pick it up in a few minutes when I come back.